Okay, so it's been a little bit of a pause right now. We've been like a couple weeks or something. Deeren went off on like an adventure somewhere. I think Richard maybe was gone or something. I don't know. People have been up to shenanigans, but we're back and we're better than ever right now. And last time we did all of our fancy shenanigans to build up to the apex of the tort code, right? We were like, check this shit out. I put my cool ass grid of new qubits. Look at these 9 beautiful qubits. I'm actually gonna make this grid 4x4 to emphasize my points. Bam, 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 bam. And remember that our qubits were along the edges of these. So if I remember right now in practice, our qubits were like along all of our fancy edges. Look at all of our beautiful ones. And remember, by the structures of the tort code, it looped around. So this qubit right here is that qubit over there in practice. So because of that, even though there's a, say, extra edge over here, this guy is the same as that guy in practice. It loops around, right? And in practice, because of that fancy structure, we were able to get some cool logical information, right? We built up this whole sort of fancy structure right now of using homology to sort of instantly prove this stuff worked. So the TLDR was, wow, look at this, I can have my plaquettes right here, and I can take the boundary of a plaquette, the boundary of the square, to get these 4 edges, and that's a stabilizer. We said that the fancy boundary group right now, so B1 is basically all the boundaries of these squares, are some of our stabilizers right now. And in the same way, we define this idea of the co-boundaries. Let's actually get some colors on this. So we said, oh, if I take this fancy dot and I ask a question, right? What are all the edges touching this in practice? I could define my co-boundary, right? Remember, when we say co, I want you guys to think questions right now. So essentially, we talked about all of these fancy stabilizers, and then we did a fancy proof, right? That in general, if I have this fancy stabilizer number 1 right here and the stabilizer number 2, you can see in this case that they overlap an even number of times, right? So if I define the red guy as X and I define the blue guy as Z, you can see they touch each other an even number of times, which means they commute, right? And remember, that was one of the fundamental things that we said we needed, is that all of our stabilizers for the code, they need to commute together. And then we use the properties of homology to show why this has to be true. Remember, we use this fancy property that if I have sort of a co-boundary of object A, and then let's say I do alpha and beta, and I do, hey, what is the co-boundary of alpha applied to beta? It's the same thing as alpha applied to the boundary of beta. In other words, you can kind of go in either direction, right? So if this sounds like some nonsense, remember all that means is, hey, if I'm asking the question of, does the stabilizer associated with this dot end up touching this red guy an even number of times, that's the same thing as taking the boundary of this red guy and asking, does it touch the dot, right? Those are 2 of the same statements. And by definition, this red guy's boundary is 0. By our definition. Remember, it touches each of these dots twice, the boundary goes away, therefore this dot can never end up touching the boundary of this red guy, therefore we go to this big idea that the stabilizers commute. In other words, they never hit each other an odd number of times. That's what we're building up towards right now. Okay, so that was the very, very fast summary right now of what we did last time. So let me actually pause and make sure everybody's on the same page when I'm talking about all these fancy concepts. That was very fast. Anybody have any questions when I'm talking about like boundaries and co-boundaries and all these fancy homology words that we talked about last time? Okay, I'm getting a lot of head shakes right now, sick. Okay.
Boundary is 0 if it's like even?
Yeah, so just to make sure that we know what we're talking about, so we were talking about Z2 homology, basically. And what we mean by Z2 homology is essentially you count everything an even or odd number of times. So when I have over here this fancy rectangle with these edges, remember that the boundary of an edge are these dots, right? The sort of vertices. And if I take the boundary of each of these 4 guys, you can see that we're gonna touch each of these points twice, right? This line is gonna have a vertex here, this line is gonna have a vertex here. We count twice, 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 twice. Because we're in Z2 homology, these cancel out. The boundary of this square is null, basically. And we actually, the fancy name for that, we call these cycles right here. So anything that when you take the boundary of it goes away, disappears, we call it a cycle. And we made a big claim. We said for any object, if you take the boundary twice, it goes away. So in other words, if I start with a square, the boundary are these 4 lines. If I take the boundary of these 4 lines, bam, it goes away, basically, right? And that logic works the other way, right? If I have a dot right here, and I take the co-boundary, those are the 4 edges that touch it, and if I take the co-boundary of this, those are all the squares that touch these guys, right? So there's a square here that gets touched twice, one's from this line, one's from this line, so bang and then bang, right? This line touches it twice. Same with this guy, gets counted twice. Same with this square, gets touched twice. Same with this square, gets touched twice. The co-boundary, in other words, if you do a co-boundary twice in the same way, you get null. So if I start with a dot, and I do co-boundary, co-boundary, you cancel everything out, it goes away. So that's the same statement right there, basically. Does that kind of make sense when I'm saying boundary of a boundary explodes, co-boundary of a co-boundary explodes? That's probably the most fundamental bit. Or do you have another, like, clarifying? Yes, no, maybe? How are we feeling?
It's like, I mean, I get the flus thing, not
oh, yeah, okay. So that's totally chill, right? Like, let's just make sure we're on the same page. So when we say right now, so I think the clarifying point is what the hell did I mean by that co-boundary stuff? Remember, co-boundary means question right now. So we're asking, what are all the things that touch an object, right? So in the same way that we have boundaries and objects like there, right? These fundamental cells, right? That are like dots and edges and squares, right? In the same way we have these boundaries, these co-boundary objects or these co-cell objects that are asking questions. Is there something touching this object, right? So when I have a co-cell dot, essentially you can think about this like a function, and essentially it says, hey, if I take a group of dots right here, right? This is maybe my collection of 0 cells, collection of dots. I can ask a question. Does it include this dot? Yes or no? If yes, it's 1. If no, it's 0, right? And I can combine questions together. Does it include these 2 dots? Yes, it does include both of them. Well, you get 1 for this, you get 1 for this. 1 plus 1 becomes 0 because we're working in Z2. In the same way, maybe your collection of dots only included these 8 and you were missing this guy, so you got 1 for this, basically, right? So in other words, the summary of all this stuff right now is that co-boundaries are asking questions, and specifically, we have all these fundamental co-objects that are asking questions, and when I say co-boundary, essentially in the same way that a boundary breaks down a dimension, right? We start with a square and we go down to lines, right? A co-boundary goes up dimensions. It says, okay, I have a dot. What are all the things that touch the dot a dimension up, basically, right? And in that case, the answer is 4 lines on this grid. Okay, what is the co-boundary of these 4 lines? Well, we go dimension up. What are all the squares that touch these lines? Well, for this line, the answer is the top square and the bottom square, right? This line's co-boundary are these 2 squares, because they're the 2 things that touch this line, right? In the same way, this line's co-boundary is these 2 squares. But notice how we counted this one twice, right? 2 makes 0, right? We're working in Z2. If you count something twice, it goes away. So this square isn't a part of the co-boundary of these lines. By the same logic, everything cancels out. Everything gets canceled out twice. And that's why I said the co-boundary of this little star thingamajig is null, right? Everything gets canceled out, basically. Everything, every single plaquette that you get gets counted twice. Does that make more sense? Okay, cool. So with all that said, we then use those definitions to define these objects, right? I said every single thing that is a boundary, every single thing that comes from take a square and break it into 4 lines, those are a type of boundary. We took all the co-boundaries as well. We started with all these dots, and we made these fancy stars, and we said those are our other types of stabilizers. And by our fancy homology definitions, they commute. Basically, they touch an even number of times. Okay, well, that was our fancy structure. And we also, the one last thing I should probably mention, remember, we also had logicals of this, right? So we had these boundaries, and remember, by our definition that if you take a boundary twice, it explodes, it goes away, right? In the same way, we could say, okay, well, the boundary of anything object, if you take the boundary of that, it goes away. There are other fancy objects that if you take the boundary of it, also go away, that aren't themselves the boundary of a square or a collection of squares, right? So for our purposes, we could say, make a fancy line like this, and notice, wait a second, if I take the boundary of this guy, it explodes, right? Essentially, this top dot loops around to the bottom, And then all the middle guys get counted twice. So this object is another thing whose boundary is null, who goes away. But wait a second, it's a different thing. And that's where our logicals came from, right? We had this bigger group of cycles, Z1, and that group was bigger than our B1 group. B1 was a subset of this. There are these extra fancy types of lines. We made these our logicals. And the reason we did that was the same reason that we like working with boundaries. This thing, by definition, commutes with all our stabilizers. What does it mean to be a logical operation? It means you change the quantum state, but none of the stabilizers catch it. And by our definition, because this guy's boundary goes away, none of these co-boundary objects catch it, basically. So in the same way, we came up with the reverse of that, the co-cycle group, basically, and we said, okay, and I should probably clear this up right now. If I went over here and I did this ladder type of thing, by the same logic as before, if I take the co-boundary of this, well, we get a rectangle there, this guy gets a rectangle up there, rectangle down there, they cancel, 2, 2, 2, loop around at the bottom, 2, this guy also explodes in the same way. So we came up with these other fundamental objects, basically, of, hey, this guy's co-boundary explodes, but it's not just these fancy little stars, or combinations of these little stars. Okay, so let's just make sure we're on the same page. So we have our fundamental boundary objects, and we have this bigger group of things that when you take the boundary go to 0, or things that when you take the co-boundary go to 0. And this is a bigger group than just boundaries of plaquettes or co-boundaries of dots, basically. Everybody feel chill about that part right now. Okay, well, with all that said, so now let's actually get to the meat of it. So this exists, it's cool, and all the theorists are happy because they got some use out of their cool donuts and all of that. But there's a problem. I want to make a physical thing that we do, right? Like my job vaguely is to engineer a thing that's useful, right? And there's a problem right here. This guy involves this magical conjecture that this dot is the same as this dot. That's kind of bullshit, right? Like how physically do you make this dot the same as this dot? Now, on some hardwares, maybe you can make some sales pitch, you can get away with that, right? Maybe you're on some ion trap type of things, and maybe you move the ions around or something, and there's some way you can concoct the strategy. But especially on stuff like superconducting, like there is a qubit on the grid, and making a connection so that this guy can do gate operations over there is hell, basically. We need something better. And that is going to be the point of today's talk. We're going to be building on our ideas of what a toric code is, and we're going to be bumping them up to the idea of a surface code. And the surface code is essentially going to be the planar generalization. Planar? I think, yes, planar. Planar generalization of the ideas of the toric code. Now, what exactly do I mean by that? Well, fundamentally, it's going to look really similar, right? I'm going to come over here, and let me make sure I don't screw around with this, right? I'm going to go ahead and draw you a fancy grid, basically. So we're going to go ahead here, have our fancy stack of dots. Look at these absolute beauties right now. And it's going to look very similar, but you're going to notice one big difference right now. And that's that the boundaries look a little bit strange. So for now, when we do our fancy surface code stuff, we are removing the assumption we can loop around. This guy is different than this guy. This guy is different than this guy. These are fundamentally different things. And first of all, let's just get our bearings on what's going on right here. So how many qubits did I just draw right now? Well, you can see that sort of on this horizontal edge, I have 1, 2, 3, 4, 1, 2, 3, 4. I have a 4 by 4. So in this case, 4 squared. On the vertical way, sort of like this, you can see 1, 2, 3, 1, 2, 3, 1, 2, 3. I have 3 squared. In total, if we count all the edges across this, there are 25 qubits I've just drawn for you, basically. Okay, so we have 25 qubits, sick. Okay, does this work then, right? And the first thing that we have to naturally answer is, this seems like it shouldn't work, right? Well, why does it seem like this shouldn't work? Well, what was the fundamental argument I gave you before for why we can do all this fancy torus code stuff? The fundamental argument I gave you was the stuff loops around, right? For example, if I had a logical right now, and I wanted to do my logical as a sort of vertical string, right, that's running straight down the loop, my argument was, hey, the boundary of this guy goes away, right? In other words, you count twice there, and the top and bottom cancel with each other. Well, that kind of seems like bullshit now. If I take the boundary of it, it very much seems like all of a sudden you should end up with stuff remaining right there, right? Okay, so that seems like it shouldn't work. Well, maybe it works in the other way, right? Maybe we can do something fancy there. So if I go over here, I try and draw it in the other direction, right? I say, okay, I can draw my fancy green line, but same problem, it seems like, right? Shouldn't I be left with something over there and something over there? That's true, and by the basic definitions I've given you, we would be kind of fucked right now. So we're gonna have to do something fancy to get away with it. And the fancy thing we're gonna do has a very fancy name that disguises that it's actually not that fancy, for our purposes at least. And here's the idea. At the very fundamental level, when I'm defining this grid, I am not gonna sort of design for these dots to be everywhere. I'm gonna sort of just tell you right now that the only dots, the only vertices on this grid are in the center here. And I'm going to specifically say that there are no dots on the ends right now. In the same way, I'm going to define some new bullshit objects for you right now. I'm going to tell you right now that if I take the co-boundary of this line, you're not, as you might expect, going to get one sort of square down here and one square up here. No. You only get the top part. There's sort of a magic void on the bottom that just makes it disappear. The co-boundary of this line is only the top part. In the same way, if I have this blue line and I ask you, what is the boundary of this line? For all intents and purposes now, the boundary is just this dot. It is not both sides. There is no dot here to be the boundary of it. There is one and only one dot. Now, here's the part where you tell me, Matt, isn't that bullshit? What the fuck is this grid I just drew? Well, there's two ways I can tell you on it. The first one is technically what we're doing here is a fancy thing called relative homology right now. You could go into a lot more details. I'm sure Deeren in the audience could say a lot more math details about what that means. For our purposes here, it doesn't actually matter that much. Here's the real thing I want you to think about. All that really matters when we do our homology, at the end of the day, is a simple constraint. If I take the boundary twice of any object, it goes to 0. If I take the co-boundary of any object, it goes to 0. That is it that we need for it to be valid homology and valid co-homology right now. In other words, even though I sold this to you as, yeah, man, think about the donut and the loops on the donut and shit, right? That's just kind of like a way to think of this stuff right here. These are the real principles that matter. And my sales pitch is, even though it feels weird to just say, yeah, there's no dots there, it results in these properties still being true. If you take the boundary twice, it goes away. Well, can we see that right now? Well, the middle ones still work, right? I take this square. I take the boundary of this square. I'll use a different color, these 4 green lines. If you take the boundary of these, double, it still blows up, exactly what you expect. Well, what about the edges? Aren't those the ones that we're scared about? Well, now maybe I come down here, and I shade in this guy. I'm gonna tell you right now that this weird plaquette thing, this boundary plaquette, is a valid guy. Well, why is it valid? If I go and I take the boundary of this plaquette, you get 3 green lines. What are the boundaries of these 3 green lines? Well, you count this dot once from this guy, you count this dot once from this sort of, I guess, vertical guy right there. Bam, 2. What about this dot? Well, you count it once from this guy, you count it once from this guy, 2, bam. The sort of boundary of these 3 lines, by the definitions I'm giving you, are 0. This principle is still holding. Even though I fucked around with the grid and I'm doing some random bullshit to make it work, the rules of homology are still true, basically, that if you take the boundary twice, it goes away. And that is all that matters for our purposes.
Co-boundary for the last one.
What's up?
Look at the co-boundary stuff.
Yeah, right? So there's actually a good point right now. Okay, well, I sold you on the boundary. I didn't sell you on the co-boundary stuff. Fair enough, right? Okay, well, let's take a co-boundary example. Well, the very obvious one is the center one, right? So center gives the four lines cancel, pretty obvious. What about the edges right now? If I go up here, and I circle this guy, I am going to take the co-boundary of this guy twice. So first co-boundary, this line doesn't exist. By definition, there are only 3 lines now. So this is going to be my actual boundary stabilizer. It's only going to have a weight 3, not a weight 4, because it's only going to include these 3 guys. And then what happens if I take the co-boundary of the stabilizer, i.e. I'm going to ask what squares are touching everything. This guy right here, there's no square up there. You're just going to go down 1. This guy goes left 1, 2. Oh my god, this died, damn. In the same way, this square, you go down 1, touch once. This line to the right 1, you also get 2. It blows up again. The rules of our cohomology are also satisfied by the definitions of the surface code. That's a really good point, right? Like if that wasn't true, we'd be very, very fucked. Okay, so it seems like at a vague level right now, our basic rules still hold. So now let's make a damn code out of it, right? So how are we gonna make a code out of this? Well, the basic idea that we are gonna go ahead and use is we need to first of all define our stabilizers, right? That's a fundamental thing. Okay, we have 25 physical qubits. I've already told you there's 25 physical qubits. Let's see how many stabilizers we need. Okay, at the very fundamental level, we need these 6 middle guys, but I'm gonna tell you there's some extra plaquettes right now. Remember, by our definition, there are these magic plaquettes, i.e. boundary plaquettes, 1, 2, 3, 4, 5, 6. Right? And these are valid. If I take the boundary of the square, you get these 3 lines, and if you take the boundary again, it goes away. These are valid in terms of becoming stabilizers. So we actually have 12 of these. And let's just go ahead and just decree right now that these 12 squares are our Z stabilizers. So we have 12 Z stabilizers. And I'll draw one characteristic boundary one so you can hold that in your head. In the same way, right now, we can talk about our X stabilizers. Well, we need dots, we need vertices. By our definition, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of these right now. Notice the bottom 3 and the top 3 are boundaries. They don't make the full star. They only make, as I'm going to draw right now, these sort of, oh my god, this marker is actually close. Okay, I guess we're doing another blue. We only make, oh, that's nice. Okay, we end up with these 3 right now, basically. So that ends up being our boundary stabilizer. Okay, and with that, we have 12Z and we have 12X. So guys, if I have 25 total qubits and I have 24 stabilizers, how many logical bits do I have? Does everybody remember math? Guys, I'm gonna be honest, it's first grade math right now. 25 minus 24, where are we at right now? We got 1. We got 1 and exactly 1 logical qubits, basically, right? Our number of logicals is the sort of total number of physicals minus the number of stabilizers, basically. Okay, so we're doing pretty good, it looks like. All right, well, if this is gonna be a valid code though, we can't just have logicals. We need a way to do logical operations, right? Like I need to sell you guys there's a way to do my X gates and my Z gates and all these fancy things. Is that still something that can be done? Let's find out. So if I'm over here, and oh my god, this marker really died fast. It's really one of these. Okay, I guess we'll sort of make it work with this right now. If I have all these fancy guys and my grid has been kind of annihilated right now, but I'm gonna try and fill it back in a little bit. If I have my fancy grid and I want to do my logical operations, here's where things get interesting. So before, I sold you on 2 different types of things, right? The first one was, yeah, you can do the vertical lines and you can do them horizontally and we can do them vertically. So here's the problem. What
I
happens?
think you want to keep your markers like that. That's why they're drying up so fast.
Oh yeah, that's probably true, I'm not gonna lie. Wait, this is like actually more engineering core right now. I'm gonna close each of these markers. Okay, so with all that said, if we're over here and I want to do my logical operation, right? Well, the first thing that we might try and do is try and do our vertical loop, right, guys? We can do a vertical loop, but there's a problem right now, right? We still have vertices here. We're gonna end up right now with boundaries at the end, basically. And what that means is it doesn't fit our definition. Our definition of all of our basic stabilizers and logicals should be if you take the boundary, it goes away, right? This doesn't meet the definition. Okay, specifically, why is that a problem? Let's actually make that a little bit more clear. Well, remember, we have our boundary stabilizers, right? So if I have my boundary stabilizer that comes from the co-boundary of this dot, you would end up with these three red. Look at that, it touches it once and exactly once. That's fucked, basically, right? So because of that, we can see that the vertical lines don't work anymore. But, okay, so crap, right, should be the reaction. What about our horizontal lines? So now we redraw our fancy grid, our beloved surface code grid, filling each of these fancy dots, right? And now we're gonna try the same thing, but the other way around. So I'm gonna shade in all the way to the end. Does it work? Well, yeah. Now there's no boundaries at the end. All the middle ones cancel by the same logic. This is a valid logical operation, basically, right? And in the same way, let's say I decide arbitrarily to decide that this is my Z logical, which I can do. It's kind of arbitrary, right? Okay, cool. Well, this commutes with all of my X stabilizers, right? If I define my X stabilizers right now to be these plaquette things, basically. So if I define, the star thing. So if I define my X stabilizers to be these star things, you can see it touches it twice every single time, right? Okay, so we have a valid Z logical, sick. Okay, what about X logicals? If I have an X logical, there's two properties that absolutely positively need to hold right now. We need to know that our X logical commutes with all the stabilizers, and then we also need it to anti-commute with the Z, because our definition of X and Z is an X and Z anti-commute, right? So we need our logicals to do that, basically, in practice. How do we do it? Well, we use the same ladder thing. But notice that ladders in this direction don't work anymore. You're gonna be left with these boundaries right now. So what does that mean in practice? It means you can only do those ladder things from last time in one direction only. Specifically, if I now go and draw vertical ladders right now, you can see it meets all of our conditions. If I take the co-boundary of this ladder, you can see that these squares at the top and bottom don't exist. These guys get hit twice. The co-boundary of this is in fact 0. So this is a part of our Z1 group, our one co-cycle group, right? If I take the co-boundary of this, it explodes. Good. Okay, what does that mean practically? Does it anti-commute right now with our Z logical? Yes, it does. It hits it once and exactly once right there. So the ladder goes vertically, the line goes horizontally. Bam, they touch once and exactly once. They work, basically. And based on that, you can see how this lines up with there being only one logical in total, right? There's only one type of Z you can do. You can do this direction Z. There's one type of X you can do. You can do vertical X. There's only one type of each logical operator because there's only one actual logical qubit being stored, not two right now. And by all of our same homology, because we built it up like this, now we have an entire equivalence class of the same stuff, right? In other words, let's go and clear this off a little bit. This is obviously not the only Z logical that works, because remember, our fundamental definition is that you can apply any stabilizer that you want to this fancy shenanigans of stuff, and it still works, right? So by our definition, we can see that, hey, I think we're defining right now the rectangles to be Z's, right? So if this is a chain of Z's, this is Z, 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 Z in practice, I can apply my plaquette of Z's to move this. So in other words, another valid logical is to apply bang, 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 sort of snake around in this other way, basically, right? I could apply another fancy rectangle down there and snake around like this. These are all the same fundamental logical operation, right? They look different, they have different lengths, i.e. different weights, right? But they represent the same thing. They both do a logical Z because they're the same up to stabilizers. And I can define this, the fancy math way, remember, was that this is our equivalence class, right? We had this equivalence of Z's where it's all the same idea of going from the left to the right up to stabilizers, up to these boxes. Same idea with our ladders vertically. You can change them by those stars, and they still represent the same fundamental x, basically. So I can define an equivalence class of x's, i.e. they're the same idea of going vertically up to these stabilizers, right? And there we go. We have defined now all of the same structures that we built up last time with the surface code. Okay, so let's pause here for a second. This is the basic part of surface code. How do we feel about this right now? It exists, it's cool, right? And by the way, one last thing, I should talk about parameters in general, right? Well, what are the parameters in general? Well, in general, it's going to be length L one way, length L minus 1 the other way, right? So in this case, we had a 4x4 and a 3x3 for horizontal and vertical lines, respectively. In general, we're going to have an L squared plus L minus 1 squared. We're going to store one logical. And what's the minimum length to get across this right now? Well, 1, 2, 3, 4, or 1, 2, 3, 4, right? So the minimum amount of x's or minimum amount of z's you need to do one of these fancy logicals is 4, or in this case, L in general. So we have a distance of L. Remember, the distance says what is the minimum number of errors that need to happen to do one of these logical operations in practice. And with that, we have a code. But we can make it better. We can make it a lot better. It turns out we can double our efficiency almost, basically for free right now. And to do this trick, this kind of mind-boggling trick, because it feels like, okay, well, we made the code, we should be done. I'm going to actually go ahead and explicitly write out for you some little circles for our qubits. And what we're going to discover right now is probably one of the most powerful techniques in error correction. What we're going to discover is that just by fucking around with the boundaries, you can make new cool versions of codes. You can make substantially better versions of codes without having to invent new stuff, but simply by just looking at how we do our boundaries. What do I mean by that? So again, I'm going to draw the exact same picture right now. So here was the picture I was trying to sell to you. I'm going to try and use this blue now because I think it's a little bit clearer. And if I go through and I draw each of these guys, remember that for now, our qubits were on the edges right now. So here's what I'm going to do. I'm going to actually explicitly draw that. Look at all of our fancy circles. You can see that in total, if I draw all of these, there will be 25 circles on the grid. And here's, if you kind of stare at this for a while, right, you really soak it in, you might start to notice something really, really cool that you could get away with right now. What is that fancy cool thing? And actually, I think to sell this a little bit better, it's going to be a little bit easier if I use a 3x3 grid. So actually, here's what I'm going to do, just to make this a little bit nicer, a little bit easier to see, I think. 1, 2, 3. Okay, we're going to use a 3x3 just to make it a little bit nicer on the eyes. So it should end up being like this. Okay, is this correct? Let's see. It takes 1, 2, 3, 1, 2, 3. Okay, and actually, this should go away as well. Okay, so this is a really baby, tiny, itty bitty code, right? Okay, cool, it exists. And if you stare at this for a while, you might notice something really, really cool right now. Let's draw an example of one of the stabilizers that we can do, one of the logicals that we can do. Well, I told you guys, we can do this sort of horizontal line, right? That's going to represent a logical operation. Well, one way you can view it is that we're doing a line right here in a horizontal direction. Another way you can notice that we're doing is if I draw this fancy rhombus-looking thing, notice what I have right here. It looks a lot like a 3x3 grid, right? 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, and it looks like on this 3x3 grid, my logical is going to be this sort of horizontal line, which if you tilt your head right now, looks a lot like a diagonal along this. Well, what do my stabilizers look like in this new picture right now? Well, if I draw these out explicitly, well, let's look at some examples. Well, over here, I'm going to go ahead and have these 4 represented my plaquette, right? Well, if I actually draw this out explicitly, I can draw these 4 and say, wait a second, this is going to be my x, right? Okay, cool. Well, what about this fancy star thing that we talked about before? So before I would draw it like, you know, bam, 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 bam. I can draw this as another square right now. That was a star, remember it came from this vertex. But we can also draw it as another square right now. That's a z. Remember, this is the same fundamental thing. I'm just drawing this in a different way. But now notice the same pattern, right? This is going to be a z over there. It comes from this dot. So that's going to be a z. And in the same way, this comes from an x, right? There's a square underlying it. So we end up with an x. What do we end up with in practice? It seems like this is equivalent to thinking about 4 squares right now. Specifically, z, x, and then we end up with x and z. Notice that our cubits are on the vertices of these squares, not the edges. So we now have these 9 cubits from that grid I showed you on the vertices right now. And then finally, okay, so it looks like this mostly transfers, but the boundaries are still kind of fucked, right? So we have 9 cubits and we only have 4 stabilizers. That seems kind of cooked, right? We need 4 more stabilizers. Where are they? We're going to invent new boundaries, and that's going to be the power of what we're doing. I'm going to go over here and say, okay, well, right now, if I applied x and x, this would be an error nobody would catch, right? This z stabilizer of weight 4 would have 2 x's on it, it wouldn't notice, and then obviously the x guy can't catch the x error, right? It catches opposite types. What am I going to do to solve that problem? I'm going to declare this weight 2 x stabilizer on the boundary. So in other words, this isn't an error anymore, it's a stabilizer. It's one of those checks that we're doing. In the same way, well, I might have a problem here. What if all of a sudden there was 2 z errors right here? This guy wouldn't catch it, this guy wouldn't catch it. We're going to make that z a new stabilizer, basically, a new weight 2 stabilizer. We're declaring that these 2 qubits, we are going to check as a ZZ stabilizer for any errors. In the same way, we can define this to be our next x and this to be our next z, which I guess I'll use blue for that. And in the same way, we now have 8 stabilizers. And notice something really cool. Why did I do this specific pattern? Well, notice once I cover this guy, this x stabilizer kind of covers any problems there. If I end up having an XX error, this z will catch it because it'll touch once on that dot. If I end up having a ZZ error down here, this x guy will catch it, right? If I have an XX error on these 2 dots, the z guy over there will catch it. In other words, all the weight 2 errors on the boundaries get caught by these sort of boundary stabilizers. And you only need 4. You can notice this pattern where it's going to count every other edge, right? Bam, off by 2, bam, off by 2, bam, off by 2, bam. It turns out, this has a fancy name. It's called the rotated surface code. Rotated surface code. And with essentially half the qubits, notice that we only need 9 right now. This original grid would need 3 squared plus 2 squared. Now we just need 3 squared, or in general, L squared. It's just a grid, L by L. So we still get our 1 logical qubit of information. And we still get a distance of 3. How do you go ahead and actually do a logical? Well, now we just have vertical and horizontal lines. So specifically, if I wanted to, right now, do, say, I don't know, let's say a z, a string of z's. Well, if I do z, 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 along here, I'm going to write this out. Z, 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 in the horizontal direction, notice none of these guys catch anything. This x has 2 z's, this x has 2 z's. Double anti-commute means commute, right? And then these boundaries aren't catching shit because there are z boundaries along this edge. In the same way, right now, you can see if I do a vertical string of x's right now, none of these middle actual bulk stabilizers are catching shit right now because I have 2 x's per piece. And then the boundaries at the top are x. X's aren't catching x, right? So that means that we can do vertical x's and horizontal z's. And it still works. What does that mean? We have a distance 3, or in general, I should probably write it like as a distance, we have a distance L code. We need, for an L squared grid, an L by L grid, we need L errors arranged in the perfect way to sort of fuck it up, basically. Now, with all that said, one thing that should be noted, so is this free right now? Did we just objectively make a better code? Well, yes and no. In practice, on hardware, this is what is done experimentally. People use the rotated surface code, not the original unrotated surface code. And the reason is you need half the qubits. You go from L squared plus L minus 1 squared to just L squared. That's pretty damn good save. It's not completely free. In other words, it seems like it should be a 2x save. Not quite. And the reason is that it turns out decoding this ends up getting a little bit harder. Now, to understand why that's true, it's time for us to finally talk about the real beast, the real monster right now, of how do we decode these things. And just to set up the picture, I'm actually going to go back to the unrotated surface code for a second, because it's going to be a little bit more clear, I think, on how it works. And we're going to talk about how do we catch our errors in practice. So let's just make sure we're on the same page. What are we talking about? Well, we have this quantum stuff set up, right? There are stabilizers. They exist. I can measure them. I get ones and negative ones when I measure, right? I get some type of true outcome thing. And the job of us now is to take these ones and negative ones and figure out what got fucked up. That's the job. Well, that sounds like it should be really easy, remember? Like, if I went back to my original code that I told you guys about, so this is gonna be my big old grid of points. So let's draw these in. Right, and actually I should probably use a bigger grid to get these points across, so I'm gonna make a big old grid this time. So if I go over here, you guys can remember all the way from that repetition code that we talked about before, that the decoding was really obvious, right? I have 3 zeros, I send you 3 zeros, you get the message 001. It's pretty obvious what went wrong, right? It's probably I meant to send 0. You do a majority vote in your heads, and you say, yeah, you just did a decoding algorithm. Well, what does it mean to decode the surface code? Well, let's think it through. So let's just first of all set up some conventions right now. So again, I'm going to declare the plaquettes to be z's and the star vertex-looking things to be x's. It's arbitrary, but I'm just going to decide that. So, for example, this is a valid z stabilizer. Wow, crazy, right? By definition, then, you can notice that I need these sort of horizontal strings to be made up of z's, because in that case, z, 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 yes, they touch once, it doesn't matter because they're of the same type, basically. So I'm gonna sort of say, do a little vertical line for z to remind us that that's gonna be our z logical right now. And then we're gonna do physical x's as the ladder right there to give us our logical x operator. Okay, sick. So we have all of our setups right now. Let's now imagine some evil error shows up all of a sudden. Okay, well, what's an example of an evil error? I don't know. Ritik, give me a letter, X, Y, or Z. What happens first?
Y.
Oh man, fuck you. Okay, so to figure out the answer to Ritik's nefarious Y, let's break it down. What is a Y right now? A Y is an X and a Z up to a phase, which means we're actually gonna have to talk about the X and then the Z, and then we can deal with the Y together. So let's start off with an X error right now. I love how I just said fuck him to his choice, basically. With all I said, we're gonna start off with an X error, and let's imagine we have an X like this. Well, what catches X errors right now? It's pretty simple. Z stabilizers, right? What Z stabilizers and X's? Well, Z's, remember, are plaquettes. Let's actually write that down just to be very clear. I'm gonna draw a little box down here and write down Z, so you can remember Z means plaquettes, right? And in the same way, I'm gonna draw a little star-looking thing, and this is gonna be our X stabilizer, right? Okay, well, we have an X, we catch it with the Z's. What stabilizers get triggered? Well, this box touches it once, so it gets triggered. So I'm gonna put a little check to say it got triggered, right? And then this box also gets triggered. So at a very fundamental level, if your decoder gets the syndrome data out and it says everything's good except for these guys report back -1 for their measurements, you know the error happened here. Bam, you just decoded the surface code. Okay, what if we have something more fancy? What if all of a sudden I have 2 X errors right now? So I have X and then X right now, and it makes this little hook shape thing. Well, we're gonna end up with the same thing. This guy's gonna get checked. This guy's gonna get checked from the X, right? The 2 guys next to it. Same with this X, check and check. Wait a second, we double checked it. Goes away. What does our actual decoder see? It sees error there and error there. And in its mind, right now, it says, okay, well, what's the most likely set of errors that could have caused these 2 syndromes to light up, basically? Well, in its head, it's probably gonna say, well, maybe it's these two x's. That is the minimum path that would get us there. Now, notice a problem with that right now. Well, you might say, okay, well, Matt, there's a problem. Well, couldn't it take this path as well? If I did x and an x, it seems like right now it should also give the same syndrome read-in, which it does. But there's a solution. Let's say our decoder is a little bit stupid and decides that, oh, it actually went down this top path, right? So it goes and tries to correct it. Remember, the inverse of any POWI is itself, so we can apply x and x to correct it. Is this a problem? We have 4 x's being applied. But guys, notice the shape. What's the shape of these 4 x's? It's a stabilizer right now. So even though we didn't apply the corrections to the same qubits where the errors happened, we ended up making a stabilizer. And because we made it a stabilizer overall, it's as if nothing happened. We, in practice, corrected the error. And this might be the most fundamental difference between a classical error correction and a quantum error correction. In classical, you have to correct the bit where the error happened, right? An error happened in the second bit. You have to flip it back. Not true in quantum. In quantum, you can fix the problem without ever touching where the errors happened. And I just showed you how that happened, right? I showed you if there's 2 errors here, you can apply 2 corrections there and fix the problem up to a stabilizer. In other words, we have all of these states that are essentially equivalent right there, right? You can apply 4 errors or stabilizers and do nothing to the state. That's not true classically. Okay, well, in the same way, that's how the x's work right now. What about the z's? So maybe I go over here and I say, there's going to be a z error on this edge right now. Well, what's going to get triggered? Well, remember, it's going to be triggered by x stabilizers. We have these little fancy star thingamajigs. These 2 stars are the ones that are going to catch it. The bottom of this guy's star and the top of this bottom dot star. So I'm going to circle that these 2 guys get triggered right now. Okay, sick. So if we get a syndrome and it looks like bam bam on the z side, we probably know the error is right there. Notice that these still make chains though. If I go over here and I then say, okay, I'm going to have z and then z right now, well, all of a sudden this dot's getting hit twice, right? Which means nothing happened. I'm going to end up with an error down there from this base guy. Remember that the boundary stabilizers kind of look like that with the 3. So this dot's going to catch it. This top dot's going to catch it, right? Essentially the star thing which is going to catch the error down there. This middle guy gets hit twice. It's as if nothing happened. The sort of fancy stabilizer doesn't catch it, basically. In practice, we end up with another chain of stuff right now, right? Okay, so it looks like we're doing a pretty good job right now. And then we would say, oh, well, surely we go and we correct this, right? So we go and apply these 2 z's and we fix it. But there's a problem right now. Now you guys can see the problem. Let's imagine right now, okay, in this case, this is like fine. You'd probably see these 2 errors and you go try and fix it right now, right? Okay, well, in general, what if I do it in the other direction right now? So if I go over here, I'm going to say right now, bam, 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 and then let me just count 1, 2, 3, 4, and then we go 1, 2, 3, 4. Okay, let's imagine now we had nefarious 3 errors right now, right? So I'm going to go over here, and I'm going to say, all of a sudden, we're going to have z, z, z. Okay. Uh-oh, that's a lot of fucking errors. What's going to happen in practice right now? Well, this stabilizer right now isn't going to get triggered, right? It gets hit twice. This stabilizer is going to get triggered. It gets hit twice. This stabilizer is going to get triggered. It gets hit by this guy once, right? Bam, bam, bam. It gets hit once. This guy lights up. Okay, so maybe we could figure out the problem. Except, wait a second. Imagine that you're on your laptop and you see only this guy light up. Well, maybe you think, well, surely 3 errors happened there. What do you probably think? You probably think instead, only 1 error happened there, right? That seems to be the obvious explanation. It's way more likely that only 1 error happened instead of 3. So what do you do to correct it? Well, you go and you apply another z, and then hooray, this guy stops lighting up, right? So guys, did we solve the problem? Is this the same as if nothing happened? What do you guys think? If we have z, 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 what does it mean to have 4 z's in a line like this?
Same thing, right?
Is this a stabilizer though? These 4 z's? What did I tell you guys? Is this a stabilizer right now?
Oh no, you need like a whole box.
Yeah, it's a logical right now. This is a logical Z.
Yeah.
So we fixed it. We can always turn off our stabilizers, but in practice, we flipped our logical information, right? We essentially in practice applied the logical Z to our qubits. That's fucked. It means we've lost our logical information. So this gives you a good way to visually see what distance means right now, right? If there's one and only one error, we can catch this shit, right? Oh no, there's an X right there. Okay, well the X triggers the Z box. We trigger this box. Okay, what's it mean if this box gets triggered? It's probably the error down there, right? Okay, we can fix it. If there's even two errors, we're kind of in a bind, right? Because you can see that there's a distance of 4 in this code. If I have X and an X, what's gonna happen? Well, this is gonna trigger, this is gonna trigger right now. That's probably chill right now, right? Okay, well, what if all of a sudden I have X over here and X over here? Okay, now this middle guy isn't gonna trigger, right? Okay, this top box and bottom box are gonna trigger, and you're kind of in a bind, right? Well, maybe these two are the ones that caused it. Maybe these top two and bottom ones are the ones that caused it. And if you guess the other way, which is like a 50-50 coin toss, because they're both way 2, you end up doing our X logical with 4. So that's the fundamental idea of distance, right? What does distance mean? Well, distance tells you that you need 4 errors to disguise something. I need to do X, 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 X for nothing in terms of stabilizers to catch it. But it tells you something else. Remember that D minus 1 divided by 2 floor right now is the number of errors we can correct. If D is 4, this means 1, basically. We can only correct 1 error. Because even though when there's 2 errors, you know something got fucked up right now, in practice though, you don't know how to fix it, right? You might guess the right way, or you might guess the wrong way and cause a logical operation, right? This tells you the threshold, basically, right? If you're above this in terms of errors, you might fuck it up when you try and correct it. And actually, you're probably going to fuck it up right now. And that's the basics of decoding. So that's what I mean when I say we decode the surface code, basically, right? So there is a surface code, we get all this data out about our fancy syndromes, and we now sort of try and work through, well, what errors are most likely to cause it? And in general, the algorithm that gets used, we're not gonna go into it right now, but essentially the algorithm that gets used is minimum weight perfect matching, which is there's some fancy ways to say, well, what is the least number of errors that need to happen to cause this? Because generally that's the most likely error that occurs. Whatever is the minimum amount of stuff that has to go wrong. And they go and they work through the fancy data and they figure it out, basically. And now you can kind of see the problem with the rotated surface code. It's still better, but if I wanted to do the equivalent of this, right, that would be essentially a 4x4 grid. So 1, 2, 3, 4, and I'm gonna draw it very shittily, but there's gonna be 16 of these fancy squares right now. Remember, they're alternating X and Z, and our fancy qubits are on the vertices now, like X, Z, and then Z, whatever the hell, right? And the idea is that now these guys will be triggered in sort of diagonal pairs, right? So if I have a Z error right there, these two guys are gonna blow up. Actually, I should probably draw it in a different color. If this is a Z error, it's gonna trigger these two guys who get touched once by it on this corner. But that ends up being pretty tough to correct. Because it turns out, in general, with this 4x4, because there's less qubits, there are more ways to get a logical operation done. And it's more condensed into the grid. Essentially, you have the same number of ways to get across the grid in half the number of qubits, which means even though the distance is the same, you still need 4 errors, the number of ways those 4 errors can happen to cause a logical operation is much more dense, which means in practice, decoding the surface code ends up being harder in the rotated surface code case. In other words, if you have a rotated surface code, the threshold for how good your gates need to be for everything to work is generally going to be lower than in the unrotated case. Okay, and that is a pretty good intro right now to the basics right now of decoding. And that was a very basic intro for decoding surface code. So there's way more I could say, but I'm not going to, about all the actual ways that people do it in practice. But that's very CS core type things. But with all that said, I've kind of with all this fancy error correction stuff, we've kind of sort of slid some stuff under the rug. And what I mean by that is, okay, so the surface code exists, the tort code exists, Shor's algorithm exists, I guess. That's pretty cool. I haven't really told you to do circuits with it, right? Like, what if I have a circuit and it applies a T gate and then an H gate and then an S gate and it does a C naught or something, right? Like actual circuit shit. All I've told you is vaguely you can do an X and a Z right now, and that's kind of it. So for this last little part of the lecture, what I'd like to do is give you a very abridged sales pitch right now on how we end up doing stuff with the surface code. What does it actually mean to do quantum algorithms with these logical qubits? Is that even doable? And how can we do it if we want to? Now to do that, we're gonna go ahead and actually sort of talk about some new notation for our stuff. And I'm gonna constantly draw new notation and then go back to the sort of the actual physical thing that's going on. So let's take a very, very baby surface code. This is gonna be, right now, a distance 3 surface code. So this is about as baby as it gets. It's just gonna be 4 of these squares, x, z, x, oh my god, z, x, and then we have those 4 boundary stabilizers I showed you. So z, x, z, x. So this is our most baby version of the surface code that exists. It's pretty cool and awesome right now. And in general, for some of this stuff, I'm going to sort of create this new abridged notation where essentially all that really matters is that this is a square. It has an x boundary at the top and an x boundary at the bottom, and it has a z boundary on the left and a z boundary on the right. But what I mean by x and z boundary, I mean these weight 2 checks. And remember, that determines the properties right now. If you have z boundaries on the left and right, that means that you have to do a string of z's from left to right to sort of have a logical operation. You do a string of x's from top to bottom. So what's the abridged notation? Well, let's just say there's an x boundary on the top and an x boundary on the bottom. And let's say there's some z boundaries on the left and the right. This is an abridged way to talk about this. And what I mean by abridged, well, it saves us the trouble of how big is this, right? Like this could be scaled up to a 20 by 20 grid. It still has this basic form of there's an x boundary, an x boundary, a z boundary, and a z boundary, right? So, okay, that's pretty nice right now. What are things that we can do with a surface code? Well, one thing we can do is we can generally make them larger right now. So I can take my 1 qubit and I can put it on a big ass grid right now. And what's my big ass grid? Maybe it's gonna be the equivalent of this like L looking shape right now. So I have my big ol' right now, let's say x boundaries and x boundaries and z boundaries and z boundaries, right? And to do a logical x, right, you string along a line all the way across there. To do a logical z, at any time right now, you can go and do a z across there. It's the same type of idea of grids of squares right now, but it's generalized in this way to talk about these longer boundaries right now. In the same way, you can talk about multi-qubit stuff right now. So one boundary that you could set up, for example, is maybe I have a z boundary on the left, I have a z boundary, and I have x boundary, x boundary, x boundary, right? And it turns out this one can actually store 2 qubits right now. So specifically, what do I mean by that? It turns out, let me draw it like this, z1, z2, z1, 2. The idea of this is essentially there are 2 possible x's in this right now. You can do a path kind of like that, or you can do another path kind of like that. And these are fundamentally different. And I'm looking at your guys' faces, and you guys seem to think that this is probably bullshit. Like, what the fuck am I talking about with this? So let's go ahead and take a step back, actually, before I continue with some of this fancy stuff. And I'm going to show you how this notation isn't bullshit. And physically, what does this mean right now, right? There is this thing. I'm trying to sell you that you can make a 2-qubit surface code patch. They like to call these patches right now. How do you physically do that in terms of the actual qubits, right? What does it mean right now? Well, the idea is essentially we want to join 2 of these patches together. And what that's going to look like, essentially, is I'm going to take these fancy boundaries right now, and then all of a sudden, let's see if I can get this right, I'm going to go ahead and get another surface code patch ready. And let's see if I can not fuck up my notation right now. Sick. Okay, so I'm going to end up with another surface code patch, which is going to be another set of rectangles. And it's going to have another dual type of structure right now. which I want to very much emphasize. And I'm gonna actually set up my fancy boundaries in a very, very, very fancy way, where essentially I have x's over here to match x's over here. Notice that these squares kind of match each other. And the idea is to make a multi-qubit thing, you end up actually connecting these together. You start measuring the stabilizers between these two. This isn't new qubits. Remember, our qubits are on the vertices right now. We're simply measuring a new stabilizer in between these guys right now, right? And the idea is by doing this, we can construct a fancy new grid right now. Actually, I think to get this fully right, I'm gonna slightly change how I'm doing the boundaries to make it work. So in reality, remember that the boundaries are somewhat arbitrary in terms of that. They need to be spaced out by 2, but you can start them whatever. So in general, the way that this would end up being structured would be something like this. So it's gonna be like bam, 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 and then it's gonna be bam. Let's see if I can get this right. Okay, something vaguely like this would be the structure. So it's gonna be X, and then, this should be Z, X, Z, and then X, Z, X. This is gonna be our big old structure right now, right? And the big idea of what we did, okay, so does this make sense? Well, first of all, how many qubits do we have, right? Well, we had the 9 right there and the 9 right there, right? These are a 3x3 grid and a 3x3 grid of vertices. So we have 18 in total. Okay, how many stabilizers do we have? Remember that we need to count the stabilizers and subtract it from our n. Okay, well, we have a 2x5 of these like block looking things, that's 10. And we have 1, 2, 3, 4, 5, 6 of these boundaries. 18 minus 16 gives us the 2 logicals that we're thinking about, right? And then finally, what about distance? Well, you can still do the same things from before, right? I could still do from here to here and do a logical z, right? 1, 2, 3, that's a logical z, totally valid, right? So the distance is still gonna be 3, basically. But we have something fancy. What does it mean? How are we gonna define our fancy logicals now? Well, now we can do fancy ass shit, basically, right? Specifically, what we can try and do right now is define new actual ways of doing our logicals. So what I could go ahead and do for you is say, okay, I'm gonna define for you an x1, where I'm gonna circle the qubits I'm talking about right here. So maybe I do an x there, and an x there, and an x there, an x there, and an x there. And this sort of snake-like thing. Notice this commutes with each of the stabilizers. It touches each of these z boxes twice, and the boundaries don't fuck with it, right? Because they're x's. X's commute with x's. So what we notice with all this work is that you can do sort of a snake thing where you go right and up, and in the same way, it's completely valid to go right and down, right? Seems pretty chill. Wait a second, this doesn't work because it touches with whatever the hell twice. Actually, is this chill? Actually, yeah, this is chill right now. This guy seems chill, except the z up here would be the problem. My bad, I knew there's something wrong. So what you'd have to do is continue it over one and then down, and it would now work. It would commute with this guy, touches it twice, this guy touches it twice. Notice, you have to sort of make it to one of these boundary x's for it to work in practice. So you have one x logical, one x logical that way. In the same way, where I don't want to make this take way too long, we can do a z logical up, a z logical down. And you can show how these commute and anti-commute in the right ways. So you can show that an x1 and a z1 anti-commutes, an x2 and a z2 anti-commutes, and these guys all commute with each other. x2 commutes with z1, x1 commutes with z2, blah, 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 blah. You can show those things physically line up with the logicals I'm defining. Okay, so in our new notation, the abridged way of talking about this is simply there is an x on the left, there's a z section, there are these x sections, and then there's a z. So I can say, okay, well, this is basically gonna look like a z, basically gonna look like a z, gonna be an x, there's gonna be like an x, and then there's gonna be a z. And that's the basic idea, right, of our abridged version of what's actually physically happening right now. This is the fancy, easy way to just sort of put it down very quickly. Now, with all that said, at any point, if you guys do want, I'm gonna sort of use this new simplified notation and talk about some of the basic properties of surface codes, just in the interest of time, because drawing this stuff for big grids, as you might guess, takes a while. But at any time, if you guys want me to break it down into physically what's happening, I could do that. If you guys are like, this seems like bullshit, how the fuck do you actually do that, right? But for now, just to save time, let's just try and do this super fast in terms of that fancy notation. Okay, so we have multi-qubit patches, we have single qubit patches, we have big ass single qubit patches. What are some other things we could do? Well, the first thing we want to be able to do is make a state. I want to make it logical 0, I want to make it logical plus, I want to make it logical 1, I want to make it logical minus. How do we do that? It turns out it's really simple. I take that grid I had before, this one I'm actually going to draw the grid because it's really easy. We have these 9 qubits, I have my stabilizers, hooray, they exist. It is as simple as starting each of these guys in the 0 state to make a logical 0. If I start each of these guys in a plus, it becomes a logical plus. If I start each of them as 1s, it becomes a logical 1. And if I start each of them as minuses, it becomes a logical minus. And it turns out there's actually a really easy way to see that right now. You might say, well, okay, well, why the fuck is that true, right? Remember that the definition of our logical is to have a string of z's. So let's say this is my string of z's. It's these 3 guys right now. If I start off with everything in this physical state 0, then by definition, if I take z cubed of, I'm just going to put down initial state right now, it will be a +1 eigenvector right now, right? Because if I have z, 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 and I apply that to the state 0, 0, 0, I get z, 0, 0, 0 out, right? Okay, so what does that mean right now?
Wait, I
Oh, yeah, what's up?
lecture, so why what's inside the get? I've never seen that.
Yeah, sorry, that was just like a bridge notation I just made up. Initial state, in this case, is...
Oh, okay, it's IS, okay.
Yeah.
I
Let me actually write this up. The initial state should be 0 tensor 9. 0
Okay.
tensor 9. So that might be our initial state, right? And the idea, and here's the key point, is, okay, so then we start measuring all of our stabilizers, right? So we measure these 4 guys, we measure our boundary 4, whatever the hell. The point is, all of those stabilizers commute with this logical. That's the definition of a logical. What do we know about 2 different measurements that commute together? They don't affect each other's outcomes, right? Which means, from a quantum perspective, we know this is true. If I measure these 8 stabilizers now, this outcome will still be the same. For our new weird entangled state, this will become like weirds afterwards, right? But this property will still hold. Z, 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 if I apply to my state, the state stays the same. Which means it acts as a logical 0 because it is a +1 eigenstate of our logical Z. In other words, we can say this will be true. In the same way, if I start with pluses right now, we can know the outcome if I apply a measurement of x to the third, right? X, X, X. We know if I do my vertical x, it will be a +1 eigenstate, and that will stay the same after we do all of our 8 syndrome measurements. Stabilizer measurements. Therefore, if you start everything in plus and you do all of your measurements, it is going to still be chill, right? It's going to end up in the logical plus state because this will still be true. X of our whatever the hell the state is, it'll be a +1 eigenvalue of the x logical. Okay, so we can initialize stuff. Cool. That's a pretty good start right now. Can we do anything interesting? Well, one thing I'd love to be able to do is entangle stuff together. How do I do C-naught type things? How do I entangle qubits, right? It seems like with all this stuff, that seems like a pretty impossible thing to do. How do I entangle these patches together? So this is where it gets actually kind of fun. It turns out the basic structure of this, actually this might be another good one to actually draw out fully, because I think otherwise you guys are going to think it's bullshit right now. So, okay, we have patch number 1, we have patch number 2, I'm just sticking with these really baby distance 3 patches just to make life easy. And imagine that we set these up beautifully right now so that this is going to be an x and this is going to be an x, right? And you could fill in xz, xz, you know, so on and so on, right? And the idea right now, when I'm setting up all my stabilizers just so, is, actually let me switch to the other blue marker, which is a little bit better. The idea is, let's imagine also that our boundary had these x's right now, right? So you could fill in the boundary from there. There's an x there, there's a z there, there's an x there, there's a z there. You kind of just count by 2s, right, in practice. And the idea is, okay, well, we have these 2 patches, and I'm sort of just not filling the details right now. What is gonna be our logical operators? Well, we'll cut into the chase, we know our logical operator is gonna end up being, well, you can do an x like that, right? X, 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 and it's gonna be chill off that, it's gonna chill off all the middle stuff, blah, 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 right? I'm now going to introduce a connecting stabilizer right now. This Z right now. So I'm going to sort of fill in the gap with this z right now, and we're going to think about what happens. Well, normally, if I didn't have the stabilizer, this x logical is chill. Now it isn't, right? Look at that. This x is going to hit this z stabilizer, this 4 right now, at one point, this corner, which means our x logicals now anti-commute with this new extra. I'm going to put z extra to remind us this is like an extra new thing we're doing. In the same way, an x logical over here, assuming that we set up our boundaries correctly, so that the x boundaries are over here, so bam, 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 there might be an x over there, right? Assuming that these boundaries match up in this way, you can see that the x logical over here also anti-commutes with this guy. So let's think about what that means. If I started off with the logical state 0, 0, i.e. this guy was in the state 0, this guy was in the state 0, right? So you did the thing I just told you of how to make them 0 logically, right? And then, okay, if I know at the start, doing this stabilizer won't change anything, then I know this should be true, right? ZE of 0, 0 is still 0, 0. What happens when I apply my x1 logical? I'm going to define it for the first grid, x1, and it's going to be x2 over there. Well, I do ZE of x1 right now of 0, 0, and you can see right now that it anti-commutes. That's what I just showed you, which means it's equal to x1 of ZE of 0, 0. And ZE of 0, 0, by definition, is 0, 0. We get x1 of 0, 0. And remember, this was supposed to anti-commutate. That's probably the important part, right? So what does that mean? In other words, x1 of 0, 0 is a negative 1 eigenvalue of the state. In other words, if I sort of clean up my notation real quick, ZE of 0 or 1, I guess I should try to clarify this, 1, 0 is going to be negative 1, 0. And by the same logic, ZE of 0, 1 is going to end up being negative 0, 1. But here's something kind of cool. Maybe you guys could actually notice. What happens if I apply both of these? Does this stabilizer notice anything? So I apply this one chain, I apply this other chain. Actually, what do you think? Does this get triggered? We count once there and once there. So there's 2 triggers on this. Does it get hit? No, right? We count. You have 2 things, right? It like anti-commutes twice, and then, yeah, right? So what do we know in practice? If I do ZE of x1, x2, i.e. the logical states of 1, 1 right now, you get back 1, 1. So what does that mean? So we just invented something weird. So this is a new measurement we're doing, and it looks like by doing this new measurement, based on the parity of these 2 states right now, we get 1 or 0. Well, what is physically equivalent to what we're doing right now? It's the fundamental measurement Z1, Z2 logical, right? Because think about the eigenvalue structure of these, right? Z1, Z2 logical, the eigenvalues or eigenvectors are 0, 0, 0, 1, 1, 0, 1, 1. The eigenvalues of Z1, Z2 right now should be negative 1 for 0, 1, and 1, 0, and positive 1 for 0, 0, and 1, 1. We just showed ZE does the same thing as this. So in other words, by measuring this in practice, we are measuring the logical operator Z1, Z2. Why is that sick as fuck right now? So here's where we do the real cool bullshit right now. Now imagine I started my states, my logical states, in plus plus for both of them right now. Well, that's the same thing as starting them in the state 0, 0 plus 0, 1 plus 1, 0 plus 1, 1, right? If we expand into Z basis.
Yeah.
Right, so if I put down all the logicals. Okay, now we do the measurement. We're measuring these guys. So what do we get? Imagine that we get a plus 1 measurement. We keep all the logical states with plus 1 eigenvalues. 0, 0, and 1, 1. What are we left with? We're left with the entangled state 0, 0, 1, 1 in practice. We've just managed to entangle logical qubits by just doing 1 extra measurement. And that's the big result. So we can now entangle qubits. And more importantly, it's actually a bigger headline result. We've just shown you can measure multi-Pauli measurements, right? We just measure Z1, Z2 logical.
With one measurement.
Right? Huh? What's up?
With
Yeah, right, exactly. In the same way, you can measure x1, x2 logical. Now, you would want the sort of connecting guy to be xe now instead of ze, and it's the same logical. So you sort of move this guy on top of this guy right now. You could do the same vibe right now for our xe logical, or we could measure our x1, x2. And it turns out, let's just cut to the chase right now, you could even do it with y's. For y's, though, there's one last fancy technique we want to talk about. And it's actually on top of this right now. So what does it mean right now in terms of what we've done? Well, one way to view it is, okay, we've done Bell state bullshit, right? Cool. Another way is these guys can fucking move now all of a sudden, right? What do I mean? If this guy has a state 0, right? This guy has whatever state, it doesn't really matter, right? If I measure this guy onto here, basically, so now in other words, I do my plus plus, it ends up in the states 0, 0, and 1, 1. They, by definition, have the same states. If this guy was in state 0 before, then and we measure this guy to be in state 0, we've moved that 0 state over there. So in practice, one way of viewing what this does at the end of the day is I start with some little patch that looks like this. I then go and extend this patch, right? That's essentially what I've done is I've extended stuff. And then I can go and measure this guy out. I can just measure everything in the z basis or x basis. And then all of a sudden, I get left with just another patch, but moved over, right? We can move these little surface code patches wherever the hell we want, basically. So, okay, these guys can fucking move all of a sudden. And just to cut to the chase, because I want to sort of wrap this up, right? On top of that, we can also even change the boundaries of it, right? So it turns out there's a transformation that you can do right now. So I can now I've basically shown you guys that I can take a little tiny patch and extend it into a big ass patch, right? And it turns out you can even fuck around with the boundaries too. So I could make some new patch where it's sort of like this, right? I have x and I have x and then I have z and then z, right? X, x, z, z. That's like the example I showed you guys before, right? In practice, what does it mean when I do this? Well, now I can do weird measurements. Instead of connecting just z parts, this is like, or connecting just x parts, this was like connecting the x parts together. You could connect z parts on top. Now, if I have a big ass qubit like this, I can do both, basically. I could take another guy, which is some kind of qubit like this, and connect z to z over there, z to x over there. And it turns out what that lets us do in practice is measure y now. In the same way, right, that if I had a logical x that triggered this guy, and a logical x that triggered this guy, right, and that led to basically z1, z2. And in the same way, if I sort of stack these guys on top of each other, and I did a logical z vertically, that led to x1, x2, think about what happens here. There's going to be some boundary guys, which I'll just vaguely draw in green or not draw in green. There's going to be some kind of boundary things like this, some equivalent squares like that. And in general, those squares are going to get triggered by an x logical right now, which means they're going to involve a z, and a z logical right now, which means it involves an x. It's going to be some kind of x1, z1 type thing, which is going to be a y1 type thing. So this is obviously a very abridged version. I'm not showing you the full mechanics, but essentially you can build on this type of thing that I showed you with the Bell measurements to do x and z at the same time to do y Pauli measurements. So now we can measure x, we can measure y, we can measure z, and it turns out, let's just wrap this up with a big point, you can even do it with multiple qubits right now. So the big thing that you build up to right now is essentially, I have a big O ancilla qubits with all of its fancy boundaries. And then I take a bunch of other patches around here. Each of these squares represent some kind of big old collections of qubits, right? I'm generalizing it so I don't have to draw everything. So maybe I have an X patch right there, right? And then it's like an X patch over there, so this measures like a Z1, Z2 type of thing, right? And then maybe over here, there's a Z type boundary. So if I do that kind of thing, then maybe this measures an X. So I can measure Z over there, I'm measuring X over there. Maybe I even have like a weird 2-type boundary, so I can measure like a Y over there. And by combining all of these onto one qubit and then measuring it, you can do big old Pauli measurements. I could do like a X on this guy and a Y on this guy and a Z on this guy. I can do big old logical Pauli measurements is the overall summary, right? I can take these big old X logical and Y logical and Z logical on qubits 1, 2, 3. And that's what the system builds up to, is that you can do any arbitrary collection of Pauli measurements across any of your logical qubits at any way you want. And you can move these guys around with that movement thing I told you. So you can reposition them to get right. And it turns out you can also change the boundaries of these guys too. You can fuck around the stabilizers, so this becomes an X boundary, this becomes a Z boundary as well. So the overall point, okay, so I told you guys at the start that this would let us do arbitrary computation, right? Well, it turns out if you want to do stuff in terms of quantum computing, right? If you want to go ahead, I guess I was on camera for a sec. If you want basically to do arbitrary gate sequences, right? Most of it is classically doable. Specifically the X's and the Z's and the H's, they're actually all classically doable, right? They're Clifford gates. They essentially just change the stabilizers you're working with. You can classically simulate all that shit. The one guy you can't classically do is a T-gate, because it doesn't commute nicely with something. It isn't a Clifford gate, basically. And it turns out the circuit to do a Clifford gate, if I specifically a T-gate like this, can essentially be broken down into a Pauli measurement of this, some collection of states right there that you're trying to do stuff with a fancy state. It's called a magic state right now. It's specifically the state 0 plus e to the I pi over 4, 1, basically, right? And it turns out, if you do this fancy type of Pauli measurement with M, you take out your measurement data, so you're gonna get a whole bunch of measurements, you're gonna get some big old measurements, and you do a couple classical corrections, you can do a T-gate. I'm going for this very fast, because this lecture's gone a little bit long right now. But the point is, you can implement T-gates with these Pauli measurements. Okay, so it looks like we're almost done, right? Okay, so what's the one last thing I haven't told you on? Okay, so to do a T-gate, you need all this Pauli measurement BS. There's one other thing I haven't told you. Okay, but Matt, how the fuck do you make a 0 plus e to the I pi over 4, 1? This has to be logical, right? How do I logically make an e to the I pi over 4 states, right? That seems like kind of bullshit. So the last thing we need to talk about before we can say we have universal quantum computation with surface codes, which is kind of the end goal where I'm trying to very quickly get to right now, is we need a way to make that specific magic state. We need, right now, magic states manufacturer. We need a factory for this shit. And it turns out you can do that for a process called, finally, state injection. So imagine right now that I have a grid of 5 by 5 qubits, right? So I'm gonna go ahead, I'm gonna draw it 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, drawn through my fancy grid right now. These are my 5 by 5 grid of things. And here's what I'm gonna do. It's gonna be a little bit weird at first. I'm gonna start off with 4 mini patch type deals right now, right? So this is gonna be my set of 4 of these guys. They're these little 6 by 6 guys right now that we're starting off with. And the idea right now that's gonna be kind of magic, right, funny pun, is basically, it turns out you can actually, when you combine these guys together, turn your logical state into any arbitrary quantum state. Right now, you can make any state you want. Well, how's that gonna work out? Well, we're gonna specifically set these guys, so the boundary of this guy is Z, the boundary of this guy is Z, the boundary of this guy's X, and the boundary of this guy's X, basically, right? And when we go and combine all of our stuff together, what is gonna happen right now? In the end, we're gonna end up with Z logicals in this direction, right? And we're gonna end up with X logicals in this direction. Okay, I've told you I've made 4 tiny little surface code patches that all work and stuff. That means our code state is a +1 eigenstate of these tiny little ZZ guys. That means these 2 qubits are a +1 eigenstate of these 2 guys. So now look at this new line. This new line has 5 qubits, right? There's 5 qubits along this line. I've told you these 4, by definition, are gonna give you +1, right? If I measured ZZ, 1, 2, 3, 4, by definition, because these codes are doing their job, you always get +1. Which means how this overall code works with our Z5 tensor, i.e. our logical, whatever the hell, Z, only depends on the middle guy of this grid. If this middle guy is a 0, it's going to be a +1 eigenstate. If this middle guy is a 1, it's going to be a -1 eigenstate. And it only depends on this middle guy. In the same way, on the x way, if you want to be a +1 eigenstate of x, you make this guy a plus. If you want to make this a -1 eigenstate, you make it a minus. And it only depends on this guy, because this guy is a +1 eigenstate, this guy's a +1 eigenstate. It only depends on this middle guy for what happens. So what does that mean in practice? If I make this guy an arbitrary superposition, alpha 0 plus beta 1, right now for this middle guy, when I do all my stabilizer stuff, I turn on these rectangles, right? So I turn on all these middle squares, blah, 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 right now, this will become the logical state. Alpha of logical 0 plus beta of logical 1, right now. In other words, the state of this middle guy, sort of turn on, now becomes the overall state, basically. And notice, this individual qubit won't keep the state, right? These middle stabilizers that I'm sort of throwing in around here, right? So this is going to be like Z and X and Z and X that turn on around here. They will absolutely fucking destroy the states right there. But the point isn't that. The point is that whatever commutation relations you had before you turned on the stabilizers, right? So you only have these 4 patches right now, these blue guys, 1, 2, 3, 4 right now. And whatever commutation relations you had with Z and X logicals, because everything commutes with Z's and X's, once you turn on the whole grid, those relations stay the same. Which means at the end of the day, the Z and X logical relations stay the same. Our logical qubit will become the same as our physical qubits because they will have the same relation to Z and X at the end. Okay, and with that, we can take our middle qubit, make it 0 plus e to the I pi over 4, 1 right now. Make a logical qubit that is 0 plus e to the I pi over 4, 1. Use it to do T-gates. And now, because we can do our T-gates, it turns out every quantum circuit can be broken down into essentially doing T-gates and then fucking around with how you measure stuff for all the other non-T-gate stuff. So that's the overall pipeline of how with surface codes, we can do arbitrary gate circuits. We can do T-gates, we do our state injection to deal with that. We can do our arbitrary Pauli measurements. I took you for a very quick walkthrough of that. And by combining those together, we can do our arbitrary circuits. Now there's one catch, and this is the last thing I'll say. I'm sweeping some stuff under the rug. Specifically, this is bullshit, because when I take this middle guy and say, yeah, man, you just make it whatever superposition you want and then put it in the state. Yes, that works, unless an error hits that middle guy. If an error hits that middle guy, you're fucked, basically, right? So specifically, however long it takes to do this, there's going to be some p probability that shit blows up and it doesn't work. So what actually happens in practice is a very fancy process called magic state distillation, where you take this state, which is probably the state you want, but might have some errors that's like not fault tolerant, that you aren't correcting for. You take a bunch of copies of this, and you do some fancy shit to manufacture really good 0 plus e to the I pi over 4, 1 states, right? You take a bunch of bad states and you can vaguely think about average them out. That's kind of not what's happening, but that's the basic vibe of what's happening, right? To make good magic states that you can then pass into it. So the overall process, in a funny sense, is essentially, you can kind of vaguely imagine there's like a factory, right? I don't know, I'm gonna try and do my best factory drawing right now, right? The factory right here goes and makes magic states. That's its only job. And then over here is our actual circuit guy that goes and takes the magic states and consumes them at some rate to actually give the output, basically. And how fast your quantum computation is just simply how fast can you make magic states, how fast can you consume magic states. And the details of that is where you actually get into the fancy shit of how do I surface code. But that's it. With that basic process, in theory, you can take any single quantum circuit, break it down into these T-gates, make your magic states, make your funny Pauli measurements, and do arbitrary quantum computation. And remember that each of these grids can can be made as big as you want right now. You can make this 1,000 by 1,000 qubits just to make damn sure that the surface code works and that your logical qubits won't get broken, right? Which means on arbitrary hardware, if you have enough qubits, you can implement any quantum circuit in existence, even if your physical gates are shit. Even if they break 1% of the time, every single quantum gate you run has a 1% chance of breaking. With this system, you can do any arbitrary length circuit, and it will work out in the end, and you will be able to make it work. And that is the sales pitch of why we're doing this quantum error correction. Okay, and that's it for today. Sick. Nice. Yeah, bro, it's like, yeah, the surface code could be yours for $9.99.99 right now, type of shit.